So we've got a second way of dealing with systems. I was going to say a second system of dealing with systems, but you know what I mean. A second approach that is algebraic, that we're going to deal with these systems to solve them. And so this one is the addition method. It does a lot of the same things as the substitution method in, what we should look for a consistent system, a dependent or an inconsistent system, but the approach is a little different. So it is the best method when all the variables have coefficients, unless you want to end up in fraction land. So if you're having a hard time solving one of the equations for one of the variables and using that substitution method, this might be the best way. The way we do this is we start by numbering those equations again. And in these ones, we're hoping that if we add them together vertically, like looking down, one of the variables should just disappear on its own. And so in this one, if I add them vertically, I'd have x plus x, so 2x, and then adding them vertically, adding equation 1 to equation 2, I get plus y and negative y. That gives me 0, right? That goes away. I've eliminated one of the variables here. I'm going to finish this up. So 8 plus 2 is 10. I can solve for my x now. I get that x equals a 5. This one, like the others, I'm halfway done. I still have to track down that second variable. So I can take this 5 and put it back into any of the equations I want. I'm going to put it into equation 1. So I'm going to say 5 plus y equals 8. Subtracting 5 from both sides, I get that y equals a 3. And so I've found my ordered pair of 5 and 3 that is the solution to this system. Again, with these ones, if we practice this addition method, what I'm going to try and do is add the two together, right? So I'd have my y's are going to wipe themselves out in here, right? Because they have the same coefficients and opposite signs. The other things I'm literally adding together. So 1x and another x gives me a 2x. That y went away. And negative 2 plus 6 gives me a positive 4. Solving for my x, I get that x equals 2. And again, only halfway done. Oops, I didn't number them, so now I don't know how to give my instructions. This time I'm going to sub into equation 2. You could sub into equation 1 if you wanted, but I'm going to sub into equation 2 because it's all positive. So I'd have 2 plus y equaling 6. I'd subtract 2 from both sides and get that y equals a 4. And so my ordered pair for this, the solution to this consistent system, is 2 and 4. Really the same, concepts of what we've been doing. It's just a different strategy to solve these. So for this next one here, if I add them vertically, I can see that I have coefficients of 5 on my x term, and one is positive and one is negative. So the top two, the y term, disappeared when we added them vertically. This time, those x terms are going to disappear because they have the same coefficient and opposite signs. So now I'll add the other things. So negative 2y and a positive 3y gives me a positive 1y, and 9 minus 11 is negative 2. Halfway there, whoops, I didn't number them again, my goodness. So subbing that into equation 1, I'd have 5x minus 2 times negative 2. I replace the y with that negative 2 equals a 9. So 5x plus 4 equals 9. Subtract 4 from both sides. I get 5x equaling 5, or dividing both sides by 5, I get x equals a 1. And putting this together, the solution is an ordered pair. That's the point where these two lines would intersect, and that would be my answer. The next one, and again, practicing this addition method, sometimes called the elimination method. I like the addition method because then literally what we're doing. 1x minus 1x gives me nothing, right? My x terms are going to disappear when I add these vertically. Negative 2y plus 3y gives me a positive y, positive 1y, and 9 plus a negative 1 gives me an 8. Oh my goodness, really? Okay, so I'm going to sub this into equation 1. So I'd have x minus 2 times 8 equaling 9. And so x minus 16 equals 9. Adding 16 to both sides. I have to just check my key because that is a big number. I get the ordered pair of 25 for my x and 8 for my y. Not so bad. The next page gives us something that's a little closer to reality. So these ones were all primed to totally work out when you just added them together. All 4 of these had one of the variables that just disappeared when you added them together. The next ones don't work out quite that easily. The other thing on this next page is that we will see those lines of truth or those lines of nonsense that represent a dependent system or an inconsistent system. So same as the approach last time. Okay, so for A, if I take a look at it, I don't have, like if I were to add them vertically, none of the coefficients would have the variables wipe out. So what I'm going to have to do with this is do an extra step. I'm going to take a look at equation 1 and equation 2, and basically I'm going to change how they look without changing their value. So if I took equation 2 and multiplied it by 2 all the way through, I could get 6x minus 4y equaling negative 44. That's 2 times everything in there. Equation 1 was x plus 4y equaling 2. So because I did that, I can see that my 4y and my negative 4y would eliminate the y variable, right? That's how I chose to treat that second equation by multiplying it by 2 so that I could match those coefficients, one being positive and one being negative. So now when I add these two together vertically, I'd get x and 6x, so 7x. My y's go away. And over here on the whole number side, I get negative 42. I'm going to keep going, solving for x. I get x equals a negative 6. I can take that and sub it into any equation I want. I'm going to go back to equation 1 with this one. So I'd have negative 6 plus 4y equaling 2. I'm going to add 6 to both sides. I get 4y equaling 8. Divide by 4, divide by 4. I get that y equals a 2. And again, pulling it all together, giving the solution, because it's a consistent system, as an ordered pair, I get negative 6 and 2. All right, we may as well do the one that's up at the top of the page here. I know they're not in order, and there's not even a B anywhere on the page. So what we're going to do with this is take a look at these. I've got my 2 equations. I'm going to try and use this addition method, but what I'd like to do is figure out how I can make this so that it works, so that it eliminates one of the variables. I can see that the first equation, if I multiplied it by 2, I could make my y terms disappear. So let's try that. We get 2x minus 4y equaling 6. I'm going to copy out that second equation. And now I'm going to add these vertically. If I add them vertically, I get a whole lot of zeros equaling zeros. That is a line of truth. That tells me that my system is dependent. It's really pretty easy to please because there's actually an infinite number of solutions. And again, what this is these 2 equations are actually the same line on the graph, right? And so each line would have an infinite number of solutions, and this system, these equations share an infinite number of solutions. All right, I think in these ones, the biggest step is that decision-making pattern of what do you do to make one of the variables eliminate itself. So in E, I have equation 1 and equation 2. When I look at these, I'm going to focus on the y terms. You could focus on the x terms. But when I see these y terms, I see that they're both positive. Well, I want one of them to be negative and one of them to be positive. If I take equation 1 and multiply it by negative 3, however you want to write that, As much as I was dropping the x for multiplication, I tend to do it here for some reason. So what I'm doing now is multiplying everything in equation 1 by -3. So x times -3 is -3x. 3y by -3 is -9y. And -2 by -3 is a +6. So the second one, I'm going to leave it as is. And now I'm going to add these ones together. I can see that I've got a 0 and a 0 and a 0. Again, I'm back to that line of truth here. I can see that this is a system that this system is dependent because of that line of truth. And there's actually an infinite number of solutions for this one. All right, so 2 more on the page. If you want to practice this decision making, the setup so that they work when you add them together vertically, I think that's a valid thing. For C, this example's here because you can actually do whatever you need to do, and you can do something to both of the equations. So I can see here, if I pick on this y, and again, I don't have to pick on the y term, if I multiply the top one by 2 and the bottom one by 3, I'm going to match the coefficient on those y terms where one is positive and one is negative. So let's see how that looks. So the first equation multiplied everything through by 2 gives me 8x plus 6y equaling 22. And the second equation multiplying everything through by 3, I'd have a 9x minus 6y equaling 12. So I've matched those coefficients on the y. If I add those, they're going to disappear. So I'd have 17x equaling 34. Big ugly numbers, grab that calculator. X would equal a 2. And again, I'm halfway done on this. I'm going to sub this into equation 2 because the numbers look smaller. Doesn't really matter what you want to do. Whoops, that's not a 2, that's a 3. It does matter if you copy things correctly though. So 3 times 2 minus 2y equaling 4. I have 6 minus 2y equaling 4. Whole lot more work on these ones. Y would equal a positive 1 in this case. So my ordered pair would be a 2 and a 1. Last one here. You can focus on the x term or the y term. This time I'm going to focus on the x term just to show that it doesn't really matter which one you look at. I can see that the x term, if I multiply that top equation by 2, I'd get a 6x minus 2y equaling 8. And what I was thinking is that that would match the coefficient on my x term and the top equation be positive, the bottom equation be negative. Oops, that's a negative sign. Plus 2y, just copying out equation 2 so that I can add these vertically. If I add them vertically, I can see that actually both of my variables go away, and that equals 3. This is a line of garbage. This is a line of nonsense. That tells me that my system is inconsistent. Tells me it's impossible to satisfy both of these equations at the same time. Tells me that they actually run parallel to each other. Tells me that there is no solution to this system. All right, so there's one more to do at the top of the page. I think it's a good idea that if you at this point really like the substitution method or you really like the addition method, you practice your skills that you want to develop. So honestly, this is a decent one that could actually be solved either way. So you could take and rearrange the second equation to solve for x and then sub that in. If that's what you want to do, go for it. Just because the notes are on the addition method here, I'm going to use the addition method in the video. So I'm going to take that second equation and multiply it, not just by 5, but by a negative 5. So multiplying that through gives me a negative 5x, a negative 15y, and a negative 15. The top equation my x terms are going to eliminate each other. That was my thought anyway. So now when I add these together, oh man, more eliminates itself. I get 0 equaling 5. That tells me this system is inconsistent. Tells me there's no solution for this system. Tells me these lines would never intersect. Tells me that they have actually the same slope and they run parallel. So these next ones, don't solve them. Some of them are super duper yucky, but you could choose what's the most appropriate way to solve them. So we have the substitution method. We have the addition method. We did have the graphing method. And I think that's great for conceptual answers. And it's great when things aren't really big numbers, but sometimes it's impractical. And so if you had on these ones to choose between the substitution method and the addition method, which would you choose for these and why? So if I had to choose on these, if I were to take and isolate either equation solving for one variable, I am going to be in such an ugly fraction land. It's going to be awful. I may be able to approach it with the addition method if I were to treat both of these by multiplying them by something, right? I could get the y terms to eliminate. Don't even try it because it's terrible numbers. Yeah, so use the addition method, and I put in my notes, unless you really like fractions. For b, when I take a look at this one, I can see that my second equation is solved for that x. So that means that it's already primed for the substitution method. It means that I could take equation 2 and sub it into equation 1 to approach that one. And for C, when I look at this, it's actually so ready for that addition method. If I were to try and solve it for X or Y, again, horrendous fraction land. And for D, I would pick substitution for this one because it's already primed. It's already easy to take this and sub it in for X. So quick reminder, with these ones, we've got the 3 different realities. We've got consistent systems where the lines intersect and we get an X and a Y, so these are consistent. We've got dependent systems that when we graphed them, they were the same, so that's an infinite number of solutions. That was a dependent system. This was my line of truth in the algebraic approaches, so 0 equals 0 or whatever it is, right? We also have an inconsistent system as our third reality. That one, there's no solution. We say it's inconsistent. And in the algebraic approaches, what we got was a line of garbage. And the example I would use is that like 3 equals 9 or something like that. And so that's really the synopsis of our system so far. We're going to move on in our linear relations and do linear inequalities in the next.